Stadiums are among the most iconic, eye-catching structures of the modern world. Symbols of local and national pride. Cauldrons of passion, where legends of sport compete and where stars of entertainment draw massive crowds. No other type of structure keeps so many people so close together and in such an emotionally charged atmosphere. So when disaster strikes, the effect can be catastrophic.
The fire spread faster than a man can run.
And disasters have struck again and again.
Some people are killed not by their fall, but by people falling on top of them.
Turning public spectacles into national tragedies.
I felt in fear of my life. I thought I was going to die.
Today, ambitious new stadiums are rising up on every continent. The engineers behind them are striving to prevent the disasters of the future by learning from what went wrong in the past.
If ever any disaster happens, then we need to learn from it.
In short, every new stadium under construction is being built from disaster. When disaster strikes at a stadium, the tragedy is played out in the full gaze of public horror. And during the past century, more than 1,600 people have lost their lives in stadiums across the world. 1902, a terracing collapse in Glasgow, Scotland, left 26 dead. 1985, Heysel Stadium in Belgium, a riot by hooligans led to 39 deaths. In the same year, a stand in Bradford, England went up in flames, claiming 56 lives. And in 1989, 96 soccer fans were crushed to death at the Hillsborough Stadium in England. But from these tragedies, engineers have learned there are three main dangers their structures must be designed to prevent: structural collapse, fire, and crowd crushes. New stadiums are determined to solve these problems through a mixture of pioneering technology, strategic planning, and radical design. All of these can be seen at the state-of-the-art mega stadium currently being built in Valencia, southern Spain. The city's soccer team is abandoning its old home, the Mestalla, because it's just not up to 21st century standards and has no room left to expand. The new Mestalla, on the outskirts of the city, will offer unrivaled views for 20,000 more fans, a capacity of 75,000. And uniquely, the city's geography has actually shaped the eye-catching exterior. Mapped onto the roof is Valencia's River Turia.
Now, our client here in Valencia has said they want the world's best stadium.
Antes que nada, tiene que ser un estadio donde se juegue bien al fútbol y donde el Valencia gane casi todos o todos los partidos.
The corners are already marked out. And builders are working day and night to complete the job in record-breaking time. No stadium of this size has ever been built so quickly. But neither the tight deadline nor the beauty of the design is the most important mission for the new Mestalla's engineers. Their ultimate responsibility is to make sure the fans who'll soon be flocking here can do so without fear for their safety. Because when disaster strikes, people who come to watch a game find themselves fighting for their lives. May the 11th, 1985. 11,000 people were packed into Valley Parade, the stadium of English soccer team Bradford City. Just before half-time, some fans in the main stand noticed a problem.
I was sitting with my father-in-law. He said to me, it was hot underneath the seat. I lowered my hand, and indeed, it was.
We saw a little bit of smoke coming up. The immediate suspicion were hooligans were setting fire to paper. At that point, the police motioned to us to go to the back of the stand.
Less than a minute later, a whole block of seats was ablaze and the match was halted.
People started jumping up out of the seats rather smartish-like, and there was the panic. First bit of panic started.
We got up, we walked along a few seats to the gap in the back wall, which took you onto a walkway. The smoke got pretty thick. That back walkway got very congested.
And then the smoke came down, the thick black smoke, which it was as if someone had turned the lights out. You could hear people screaming, shouting. I got down on my hands and knees because it was so thick. I actually crawled over someone, whether they were alive or not, I don't know.
The toxic smoke was now poisoning the trapped crowd, and with each second, the flames were coming closer.
By this time I was getting to a stage of panic, and then it was as if someone had switched the lights on. And I looked back to where the light was coming from, and it was the fireball was coming along the corridor.
The stand's roof was now on fire.
It's described by an onlooker as the fire spreading along the stand faster than a man can run. Those of us who were up there could just about walk, so that for many of us, the fire has spread above us, below us, and beyond us.
As soon as I saw the fireball, I stood up and started to run. I thought, this is it, you've got to do something. And it is true what they say, your life flashes before you.
Both Peter and Paul made a desperate dash back through the burning stands, down to the pitch.
That the temperature rose as high as 900 degrees, which I understand is something like the heat in a crematorium.
Even on the pitch, it was hot enough for some people's clothes to spontaneously combust.
The whole period from that first flame to the entire stand being on fire top to bottom took a fraction over 4 minutes. If you weren't out before that 4 minutes, you were never getting out.
"56 people died. Immediately afterwards, investigators began to search for the causes of the disaster. They had two big questions. Why had so many people failed to escape the burning stand? But first of all, how had the fire taken hold so quickly? One factor was obvious. The 80-year-old stand was built mostly from wood. Forensic analysis showed a cigarette or match had fallen through a gap in the floorboards. In the space underneath, litter had been allowed to build up. Old newspapers and food wrappers were easy to ignite, and the fire could build invisibly before anyone knew of its existence. In the immediate aftermath of the Bradford fire, wooden stands across the UK were condemned and demolished. Nearly half the clubs in the English Football League had to close some of their stadiums. And since Bradford, any new stadium has to make sure every single material is fireproof or protected. Jay Parrish, one of the designers of the new Valencia arena, has been creating stadiums for over 30 years. What went wrong at Bradford has shaped everything he's built since.
If ever any disaster happens, then we need to learn from it. We've got to find out why did it happen, and more importantly, what do we have to do for the stadiums we're designing now to make sure that we don't make the same mistake.
Building a stadium from wood is one mistake that of course won't be repeated in the 21st century. At the new Valencia Stadium, like all other modern examples, the key building material is the most fireproof known to man, reinforced concrete. But to give this design iconic appeal, the team wants to clad the whole exterior in steel. And that creates a challenge because steel melts when it reaches a high enough temperature. So the project's fire engineer has to find a way of stopping the metal collapsing if fire breaks out.
There are a lot of different methods you can use to protect steel. One of the methods is boarding it up with a fire-resistant boarding. That's cheap and ugly, and it doesn't go with the image of the stadium. So what we've opted for here is an intumescent paint, which to the public, you wouldn't know that it's protected.
A simple demonstration shows what this amazing flame retardant technology can do. On the right-hand side is untreated wood. In the middle, it's been painted with normal paint, which burns even faster than bare wood. But on the left-hand panel, the intumescent paint behaves differently. It expands into a layer of charcoal. Less than a millimeter's layer of paint swells to 20 times its thickness. This stops heat being conducted and stops oxygen feeding the flames. After 6 minutes, both the other samples are burned through and the conventional paint is releasing toxic fumes. After 45 minutes, it's total destruction for the untreated material. But the intumescent paint not only keeps the wood from burning, it's still cool enough to touch on the back. Valencia's steelwork will be protected by intumescent paint for up to 2 hours at its most vulnerable points. But as well as the steel and the concrete, the stadium needs a material for its roof. And choosing the wrong one could have fatal consequences. One of the main causes of death at Bradford came from above the fleeing crowd. A wooden framework had been coated with something even more combustible: bitumen. It caught fire with horrifying speed, released toxic fumes, and dripped burning tar onto people's heads.
Discover the past with exclusive history documentaries and ad-free podcasts presented by world-renowned historians, all from History Hit. Watch them on your smart TV or on the go with your mobile device. Download the app now to explore everything, from the wonders of ancient Pompeii and the mystery of the princes in the tower to the life of Anne Boleyn and D-Day. Sign up via the link in the description.
As well as something fireproof, the Valencia design calls for a material that's lightweight and stylish. The architect's choice sounds dangerously flammable. It's a kind of plastic, polytetrafluoroethylene, or PTFE for short. But Jay Parrish and the Arab team have used a similar plastic before to cover the whole of this stadium in Munich. Locals call the Alliance Arena the rubber dinghy. Shared by 2 different teams, the whole thing changes colour according to which is playing. This chameleon skin is made of air-filled bubbles of ETFE, a close relative of the plastic planned for Valencia's roof. When the material was first proposed, the Munich Fire Department responded with a long list of safety rules that the plastic would break. So the engineers had to set up an elaborate series of tests to prove that their plastic wouldn't be dangerous if fire broke out.
There's a bit of a misconception about the concept of an ETFE roof. It's almost like cling film. If anyone's ever used cling film to put over bowls of food, if you ever put a match underneath a piece of stretched cling film, what happens to it is it punches a hole straight through the cling film, and the cling film melts away from the ignition source. Exactly the same thing happens with ETFE in a roof. As soon as it gets hot enough in the middle, and actually it's about 200 degrees Celsius, and the ETFE will melt and shrink away from the ignition source. And it will continue doing so as the fire builds.
The roof material vaporizes, giving the fire nothing to feed on, so it can't take hold as it did at Bradford. The plastic had passed its test. And when it opened in 2006, the Munich Arena was rated one of the best stadiums in the world for fire safety. It's an achievement Valencia's new stadium is determined to equal. But the absence of fireproof materials wasn't the only reason so many people died at Bradford. Nearly all of the 56 who perished had been trapped in the burning stand. Why couldn't they escape? 4,000 fans had tried to get out at once, but whichever direction they fled, they found obstacles in their way. To reach the most obvious place of safety, the pitch, those in the seats had to jump down one wall and climb over another. Hundreds of other people instead tried to get out the way they'd come in. They knew that beyond the corridor at the back of the stand lay the safety of the street. But they found the doors and turnstiles had been locked to stop people without tickets coming in. Only at the end furthest from the fire was there a single open exit.
Of the 56 people who died, the largest number died in that top corridor, near the turnstiles or near the gates that were not open.
Stadiums built after Bradford have to make sure the crowd can evacuate before the fire becomes a danger to them. So although Valencia aims to pull in huge crowds, as important to its design is the speed they can get out.
At full capacity, the stadium would have 73,500 people in it. We've designed the evacuation system to get that full population out within 7.5 minutes.
The 48,000 people in the middle and upper tiers will be served by over 150 exit staircases and ramps. The rest can exit at any point around the stadium, straight into a wide concrete concourse. All then get out to the street from any of 24 exterior stairs.
The key thing is to maintain a fluid flow and get people out of the stadium quickly.
The challenge for engineers is to make precise predictions about evacuation time while dealing with unpredictable human beings. So crowd behaviour from real situations like Bradford has been studied intensely and has now been fed into computer simulations. These can help fire engineers test their evacuation plans.
We're now in a position where we can use predictive tools to assess what kind of incidents could occur in the future. The first aspect that we consider is means of escape, which is extremely important for stadiums, obviously, because of the number of people that we have around. There are probably the most densely populated buildings in the world, and all these people have to get out.
It may seem incredible that a machine could ever predict the behaviour of real people. But this software is so sophisticated, it actually gives individual members of the crowd different personalities.
What we always do is make sure that the people that we're modelling includes people who've got reduced ambulance, people who might be a little bit older, people with children. What you see in this particular situation is people that are unhappy with their particular position in the queue. Generally, 8 minutes is the bar that we won't exceed because people start to get a little bit agitated and not really to like to queue more than 8 minutes.
Of course, the longer it takes people to get out, the bigger a fire will become and the greater the danger. So the engineers have to predict not only how people will behave, but also how the flames and smoke will behave.
This is a recent project which is actually modelling a concert scenario. So we've modelled a very large fire on a stage, and we have a domed roof over the top which is containing all the smoke inside the stadium. And everything inside that layer is basically deadly. The highest person in this bowl is sat just up at this point here. So what we have to ensure is that these people have got enough time to evacuate before conditions in the bowl become dangerous for them.
The interaction between crowd and structure is at the very heart of stadium design and of stadium disasters. It's what makes stadiums unique. They're not just concrete and steel, they're also flesh and blood. No other type of structure packs so many people so close together for such an extended period of time. But when individuals turn into a crowd, unstoppable forces can be unleashed. So above all else, stadium design has to manage the dynamics and dangers of crowds. It's a lesson that was learned the hard way at the first major stadium disaster of the modern era. When it opened in 1900, the Ibrox Park Stadium for Glasgow Rangers was the largest purpose-built football stadium in the world, with a capacity of 80,000. 2 years later, the ground was packed out for an international match between Scotland and England.
Suddenly, something gives way on the terracing, and people fall, they describe it later, like through a trapdoor. And they don't just fall down onto the ground. They've banged their heads, one guy is hanging by his foot. Some people fall down onto the concrete below and are killed not by their fall, but by people falling on top of them.
26 people died. More than 500 were injured. The terraces that shattered were built from wood, supported by steel. But the engineer seemed to have made some mistakes in his calculations. What he had not properly factored in was the live load, the people it had to carry. And the timber beams were stressed not just by the weight of those people, but by the force of that crowd's movement. Shortly before the stand broke, there had been a surge of fans straining to get a better view of the Scottish team. For most large structures, human activity is actually insignificant. Much more important when designing a bridge or skyscraper is the dead load, the weight of the building materials. The biggest task is making sure the structure can support its own weight. But Ibrox made it clear that stadiums face unique engineering challenges, which is why a few years later, the designers of London's new Wembley Stadium tested their live load calculations by inviting a crowd of human guinea pigs along before the opening. Over the decades, engineers have become increasingly knowledgeable about how materials and designs will withstand live loads. But collapses have occurred more recently. In 1991, 17 people died and 2,000 were injured when a temporary stand in Corsica collapsed. Just like at Ibrox, the stand simply didn't have enough supporting cross joists for the number of people it was expected to carry. And in 2007, a 3-metre hole opened up in an upper terrace of a concrete stadium in Salvador, Brazil. Soccer fans plunged 15 metres to the street below. 8 of them died. These beams are destined to hold up the middle seating tier of this stunning new sports stadium being built in Valencia, southern Spain. But although this reinforced concrete can easily cope with a load of 800 kilograms per square metre, a crowd weighing a lot less could still threaten its structural stability.
When you look at them, you think, well, how on earth could you get something that's as big as that and as massive as that to actually move at all? You know, if I jump up and down on it, it doesn't really do a lot.
But the top tier of this stand in Nuremberg, Germany, clearly is moving, and alarmingly. It's because the crowd is jumping in rhythm, bouncing at the exact rate per second that triggers the reinforced concrete structure to vibrate as well.
Every element of the building has its own natural frequency. If you hit it hard enough, it will oscillate at that frequency, a little bit like a string on a guitar, for instance.
The problem affects an overhanging balcony, cantilevered seating tiers. The lack of any supporting pillars underneath makes it more sensitive to crowd movement. In 2000, the vibration problem was noticed at a major European stadium.
Next tonight, the fears about safety which have closed part of Liverpool's Anfield ground.
The movement, caused by excited Celtic fans jumping up and down in the recently extended upper tier, led to urgent safety checks.
As Anfield underwent emergency building works, engineers were beginning to realise that longer cantilevers were particularly at risk. So the Millennium Stadium in Cardiff, which opened around the same time, had reason to be worried. It features some of the longest cantilevered stands in the world, up to 14 metres unsupported. What really caused the engineers sleepless nights is that it regularly hosts huge concerts. And music is more likely to get people moving in rhythm. Experts fear dancing could lead to disaster, even though the vibrations couldn't cause the stand to collapse.
As people jump up and down, so that stand will start to bounce. Now, structurally, it's very sound. It's stable, it's not going to fall down. But the 15,000 people who are actually on the stand as it bounces up and down don't know that. And the concern is, of course, they may well panic, they may rush to an entrance, there'll be trips and falls, and that's where injuries will occur.
So any disaster would be caused by fear of a collapse rather than a complete structural failure. A crowd could never jump forcefully enough to actually break a modern stand, but for the people underneath, it would still look like the roof is falling in.
So to reassure them, what you do is you put these props down, and actually it stops the building from moving. So it reduces the amount of flex in the floor, and therefore the people are reassured.
The Millennium Stadium was fitted with 54 of these hydraulic dampers. Kept tucked away during sporting events, they're brought out when the arena switches to concert mode.
It takes about 5 days, 3-man crew, so it's a very labour-intensive job.
It's an effective but low-tech solution. To avoid this time-consuming work, the team have decided that not all musicians require extra structural support.
People like Rod Stewart, the Eagles, I mean, they're quite sedate bands, quiet. People tend to listen to the music and not move around. Now, look at Oasis, U2, Coldplay, different kettle of fish. I mean, that's a really active crowd.
And as well as being hard work to put up, the columns block the view from some seats. The new Valencia Stadium doesn't want these problems with pillars, so the designers have returned to cantilevered balconies. Their solution to the risk of vibration is to strengthen the structure at key points.
What we do is actually model how it will react to people jumping up and down, and that gives us a more efficient design because it allows us to place stiffness exactly where it's required in the structure.
But building structures strong enough to bear the load of a crowd is only part of the engineer's challenge. They also have to design structures that will manage and control crowds, because above all, the crowd needs protection from itself.
What's being built here today is a lot of leading-edge engineering. It may seem pretty complex, but actually it's not the biggest challenge for us. The biggest challenge is how do we deal with all the people, and in particular, the behavior of crowds.
The most dramatic and visible challenge posed by a crowd is when a small minority deliberately causes trouble. Hooliganism has in fact rarely led directly to deaths in sports stadiums. But there was one terrible occasion when it did. May the 29th, 1985. Italian team Juventus were playing England's Liverpool in the European Soccer Cup final at the Heysel Stadium in Belgium. Among the supporters of both clubs were gangs of hooligans. Throughout the day, these gangs had been fighting with each other and the police. Shortly before the match was due to start, a group of Liverpool hooligans charged into a Juventus area of the ground. Italian fans beat a retreat in panic, but they ended up trapped in a lethal crush. Some desperately started to clamber over a high wall, but the wall collapsed under the pressure. In the crush and the chaos, a total of 39 people were killed. Politicians and police were determined to stamp out football violence. Stadiums were redesigned to keep rival fans away from each other and off the pitch.
We went through an era when the solution that people proposed in many parts of the world was to say, well, if we have a problem with people causing violence, they'd shut them away in pens so that we can control them.
High fences appeared at many grounds, some topped with razor wire. Fans hated them.
That's nothing to do with safety. That was a way of saying, you are a potential problem, we're going to cage you in.
Fencing was a crude design solution to a complex social problem and led directly to the worst stadium disaster in Western European history. The Hillsborough Stadium in Sheffield, England, was chosen as a neutral ground for a big competition match between Liverpool and Nottingham Forest on the 15th of April, 1989. The stadium featured a typical anti-hooligan design. High fences divided the terraces up into pens and protected the pitch from possible invasion. But well before the 3 o'clock kickoff, the central pens at Liverpool's end of the ground were becoming dangerously overcrowded.
In these two pens, people were just absolutely jammed together. By the 20 to 3, it was already twice the safety certificate number.
One of the people caught in the crush was 17-year-old Gary Burns.
You just assume that then somebody would say, "All right, that pen's full, shut it off." And then it started getting more uncomfortable. And then you suddenly realised that you couldn't move. You were pinned to one position. If you hear a woman screaming like you think, well, someone's going to come and help in a moment, because there were people obviously in distress, there were people shouting out for help, but there was no one there.
Unaware of the problems inside, other fans were still trying to get into the overcrowded terraces. But because only a tiny number of entrances had been allocated for 10,000 ticket holders, a dangerous crush had formed outside as well.
The guy outside radioed in and said, I'm seriously worried about injuries, possibly even worse than that out here. There's no way we're going to get these people into the ground anywhere near the kickoff. Frustration is rising.
At 5 to 3, to relieve the bottleneck, police made a fatal mistake. They opened a wide gate that was only supposed to be used for exit. Thousands of fans entered the stadium at once. No one had warned them of the situation inside, so they all headed directly to the overcrowded central pens.
I want you to think here of a piston going into a chamber which is already full.
Inside, people were pushed so tightly together, their lungs became compressed, and they began to suffocate.
And it's the weirdest feeling, so surreal, of being outside in the open air with the sky above you, but you can't breathe. You'd end up gasping for breaths. There were times when you could inhale, but then the pressure would squeeze a bit more and you couldn't actually exhale. I felt in fear of my life. I thought I was going to die.
As the game kicked off, thousands of spectators were fighting to stay alive.
People immediately started lifting their youngsters to try and get them out of there, and people were grabbing them by the hand and pulling them out. Others were manfully trying to climb this overhanging fence. Others were actually trying to break it down.
When they started trying to escape out over the perimeter fence, the police interpreted this as a pitch invasion, as hooliganism, and started pushing them back.
The duty of care, which is actually the primary duty of the police in policing events of public nature like this, the duty of care didn't really exist in any realistic sense at all. It was all about, these people are trouble. It wasn't just Liverpool, it was football fans are trouble, and these are Liverpool fans, that's even worse.
Too slowly, the authorities realised people were dying.
Bodies everywhere, lifeless bodies, bodies that seemed so limp, people being carried out and put into the grass.
96 people died, more than 400 were injured. What could have led to such extreme overcrowding? The official inquiry blamed poor design, poor planning, poor management, and catastrophic crowd control. And yet, tragically, Hillsborough was by no means the first stadium crowd crush, or the last. All over the world, chillingly similar disasters have occurred for the same reasons. In 1996, in a Guatemalan stadium, 76 people died at a World Cup qualifying match. Once again, most died from compressive asphyxia. The crush stopped their lungs from working. Even at Heysel, suffocation was in fact the cause of most deaths. Although hooligans had triggered the fatal stampede, no one actually died as a direct result of fighting.
The mass fatalities, the cause of death has invariably been constrictive asphyxia. That's where you can't breathe. The pressure around you is so immense that you breathe out, you can't breathe in again, so you suffocate to death. After 30 seconds, you lose consciousness. After 6 minutes, you're brain dead.
Attempting to prevent this horrible form of death has become the life work of Professor Keith Still. He advises everyone from Olympics organisers to the Saudi Arabian government on how to move masses safely. A mathematician by training, he's brought a scientific approach to the problems that occur when individuals turn into a crowd.
Above 1 person per square metre, we start to behave as a crowd. Your options for choice start to become reduced. Your lines of sight become reduced. We can't take whole paces. Everyone seems to know where they're going, so we'll just follow on. It's going with the flow, in effect.
At this point, individuals have become powerless to influence the crowd they're in. The whole is bigger than the sum of its parts and more dangerous.
Progressive crowd collapse happens when one person falls over. He hits the ground, taking 2 or 3 with them, and then you have a wall of people.
The mistake for decades was to try to blame people, like hooligans, when crowds were crushed.
It's not the crowd's fault. It's a failure to control the flow. It's a failure to understand the dynamics of the crowd in those confined spaces. Assuming that the crowd can be controlled and coerced, rather than designing around the crowd's needs, was the biggest mistake in the past.
At Hillsborough, overcrowding had created a force so great it broke metal barriers. But such pressure would never be able to build up again, thanks to a change in stadium design, which took place immediately afterwards.
First most visible sign of progress after Hillsborough was the perimeter fences started coming down.
Sometimes the best engineering solutions are the simplest. Hillsborough had proved that a crowd can't look after itself. It needs to be managed. So engineers had to develop new technology for monitoring and moving people. Some of the most state-of-the-art systems in the world can be found at Anfield, the stadium of Liverpool Football Club, whose fans died in the 1989 disaster. Crucial to the design of any modern arena is something most spectators barely notice: the control room.
So this is the hub of all the operation for a match day. Without this, you haven't got a stadium.
This nerve centre surveys the whole stadium, both visually and electronically. It's designed to make an overcrowding disaster impossible.
Every turnstile, when everybody goes in, gives you an electronic pulse. So it can tell you how many people have come through that turnstile, how many people are in each area. And the idea is that's giving you a build-up as to the flows of what's coming in, so you don't end up too many people in one section. And if you did get to that number, bells would go at the turnstiles and automatically you've got to close them.
The threat of violence has been eliminated not with fences, but by identifying, arresting and banning any troublemakers.
There are 56 cameras throughout the stadium, so you can see numbers, people, movement, crowd dynamics and any incidents.
The 45,000-seater stadium also brings in a team of around 1,200 people to run each match. That's one member of staff for every 38 fans. Perhaps the most significant change to stadiums after Hillsborough was also the most unpopular with fans. At Anfield, it meant losing a feature of their ground that had become legendary. The Kop once held 20,000 people, all standing on terracing.
If you look at the pattern of disasters, of accidents, Bradford apart, they all take place on terracing.
Standing terraces were regularly the site of everything from mass fainting to broken limbs, as well as deaths. But in the 1990s, all major football stadiums in the UK were forced to replace them with seated areas.
Injury levels have fallen very dramatically. You know, if you're in a seat, you can't sort of rush forward so easily. When somebody scores a goal, you don't get these sort of great pile-ups at the foot of a barrier.
And the same policy quickly became the norm across the world. It's compulsory for venues hosting international competition matches. A side effect was that some legendary arenas have seen their capacity slashed. Rio's mighty Maracanã once held just shy of 200,000. That's been halved to 95,000. But when it comes to saving lives, the UK's experience can't be argued with. Not one person has died in a crowd crush since the end of standing terraces there. So it's no surprise that the new Valencia Stadium will be an all-seater. If the 75,000 seats, which will soon be laid on these beams, were laid end-to-end, they'd stretch for over 35 kilometres. But to be sure to prevent a crowd disaster here, the designers have to ensure people stay in their seats.
What happens when the action gets really exciting? Everyone has got to have a good view of it. Otherwise, if they can't see it, they're going to stand up. And if someone in front of you stands up, you have to stand up. Here, as with every stadium, we design every row individually. We actually start from first principles, drawing what we call sight lines from the goal line or the touch line to the eye of each spectator.
The designers then work out how much higher each spectator needs to be to see over the head of the person in front.
The challenge for us is to make sure that everybody in the stadium has a great view.
Good stadium seating ensures a win-win situation. The sports fan knows they can enjoy their game without obstructions. And the authorities know that they're managing a crowd that's much less at risk. Even though human factors are the most immediate dangers stadium engineers worry about, the sheer size of these structures also makes them vulnerable to the forces of nature. Valencia's design features an eye-catching curved facade, but that creates a problem. The non-standard shape is not covered by standard regulations for wind loads. So, to prove their design would be safe in a storm, a detailed scale model had to be built and placed in a wind tunnel. The fear was that sections of the facade could blow off, or gusts could set off destructive vibrations. But the design passed the test. It's strong enough to withstand even a freak storm. Jay Parrish learned to anticipate natural disaster and design accordingly as part of the team who created the most ambitious stadium the world has yet seen. The designers of the Beijing Olympic Stadium feared it could be destroyed by a natural disaster, an earthquake. The devastation witnessed in Sichuan just months before the 2008 Games was a tragic reminder of the power of these seismic forces. Beijing too is in an active earthquake zone. If a strong shock strikes the Olympic arena, the lives of up to 91,000 spectators would be at risk. And stadiums present a unique challenge to seismic engineers. Unlike other big buildings such as office blocks, their size is spread over a vast area. The bird's nest is over 1/3 of a kilometre in length. During a quake, the ground beneath it would probably move differently at each end of the structure, creating a tension that could pull it to pieces.
The inside of the stadium, the concrete stands, the concourses, that's been designed as a number of separate sections. So there'll be one here, there'll be another one here. And by doing that, we can allow each of them to move independently if there is an earthquake.
The concrete seating bowl of the stadium has been split up into 6 segments. In between them, the builders have left gaps of up to 2 centimetres. In an earthquake, each of the sections can move individually. But the steel skeleton that gives the bird's nest its nickname couldn't be divided into separate segments. It has to stay as a continuous structure because it's self-supporting. Columns to hold it up inside would have blocked the views for spectators.
We had to come up with a way that we could make this behave well in earthquakes. And we did that by making it entirely separate from the rest of the building. Any contact that it might have with the inside of the building is by a flexible joint. By doing this, the whole outside can move quite happily on its own.
These flexible joints prevent the more rigid concrete interior tearing the steel skeleton in different directions. Steel is naturally a lighter and more flexible material than concrete. But the designers still had to make sure the component beams wouldn't break during a quake. So the project's seismic engineer decided to pit the structure against forces so great they're off the Richter scale, using a computer simulation. Anything turning from blue to pink was bad news. It indicated a beam or member had broken. So many did break that the structure collapsed. But identifying exactly where this happened taught them how to make the stadium safe.
By identifying the members that have been damaged completely without any strength remaining, and those have been damaged severely, we can just strengthen those members that are necessary.
When the test was run again on a structure where just the few vulnerable beams had been strengthened, it didn't collapse. As a result of these tests, the real thing should be standing for many centuries to come.
The most severe earthquake we have considered in our design is a very rare earthquake event, which happens once every 2,500 years.
The Bird's Nest is just one of a new wave of hugely ambitious, eye-catching stadiums. Competing with it for the world's attention are the likes of the Sapporo Dome in Japan, which can slide its soccer pitch outdoors and swap it for a baseball field. And soon Europe's largest stadium, Nou Camp in Barcelona, will undergo this radical transformation and grow its capacity to 110,000 spectators. So when Valencia opens its new stadium in 2009, the designers know it must be more than just an arena for sport. It must compete with these other iconic structures and become an instantly recognisable brand for both Valencia's football team and the city.
What we're looking for is to create something which is not just a building, we're looking for an icon. It's like a cathedral. It's one of the few buildings that actually has soul.
But designers today are only able to concentrate on dazzling forms and guarantee spectators an exciting experience because engineers have worked so hard to solve the dangers that stadiums once presented. 21st century sports stadiums have truly been built from disaster. We are living in one of the great ages of bridge building, with engineers creating higher, longer and more spectacular structures than ever before. They defy gravity and reach out across great divides. Driving across them, we take them for granted. But when bridges go wrong, the consequences are appalling.
It looked like a war. There's people screaming everywhere, blood, cars sinking, people in them.
And it shakes our faith in the world.
I mean, I still sometimes am trying to wrap my head around why I'm alive still, because I thought I was dead.
Now, bridge builders must ensure that these modern marvels don't fall prey to the disasters of the past. They go back to those disasters and examine them forensically, like a detective at a crime scene. Previous mistakes are analysed and new technologies devised to combat past failures. In short, every major bridge under construction is being built from disaster. Bridges showcase some of the most awe-inspiring engineering on the planet. Engineers can now build bridges of astonishing height, length and beauty, and designers try to outdo each other with the boldness of their creations. But increased ambition means overcoming increased risk. And when they don't get it right, the results are catastrophic. In 1940, the Tacoma Narrows Bridge in Washington State was ripped apart by the wind. In 1970, a bridge in Australia collapsed during construction, killing 35 workers. In 1980, the Sunshine Skyway Bridge in Florida was destroyed by a freighter, plunging traffic into the water. And as recently as 2007, an interstate bridge in Minneapolis suddenly collapsed, claiming 13 lives.
Bridges are not supposed to fall, and there's not supposed to be a collapse like this.
When bridges collapse, engineers have a gruesome blueprint of what went wrong and learn vital lessons from those failures. This means that new bridges, however bold in design, will be disaster-proof. One of the most ambitious bridges in the world is Stonecutters Bridge, currently under construction in Hong Kong. When completed in 2009, this stunning super bridge will be the second longest bridge of its kind, with a main span of over 1 kilometre. Stonecutters will span the entrance to the world's busiest container port and will allow cargo to be moved rapidly in and out of mainland China, providing a vital artery for the country's expanding economy. The bridge is also intended to create a monumental addition to Hong Kong's ever-changing skyline.
Many cities worldwide are identified by their bridges, such as the Golden Gate Bridge in San Francisco, the Tower Bridge in London, Sydney Harbour Bridge. Stonecutters Bridge will achieve similar iconic status when it's completed.
But the engineers behind this Golden Gate of the East have more on their minds than just function and beauty. They also have to build against a whole range of disasters which could befall a bridge of this kind. They have to worry about the complex aerodynamic environment of the surrounding terrain, protect against the corrosive nature of the salty air, prepare for the onslaught of the annual typhoon winds, and plan for the threat of being hit by giant container ships. No one expects a bridge to fail, but when it does so with spectacular and catastrophic consequences. This is Minneapolis in the American Midwest, on the banks of the Mississippi River. On August 1st, 2007, it became the site of one of the most shocking engineering failures in American history. At 6:05 that evening, Lindsay Peterson was driving home from work across the Interstate 35 West Bridge.
I usually took that route. I mean, it was very common for me to take 35. My job is right off of 35, and my home is right off of 35.
Lindsay found herself in slow-moving traffic in the middle of the bridge when there was a sudden noise.
I actually heard this really distinct sound of metal snapping, and within seconds after that, I was falling.
The bridge had given way beneath her.
I thought that I was gonna die as soon as I landed. I thought I would land on the cement or something and it would smash me like a pancake.
There was a team of construction workers on the bridge at the time of the collapse. Nothing alerted them to what was about to happen.
I was moving a piece of equipment and the bridge started to shake, which it normally does when a heavy semi goes across or whatever, and it shook, and then all of a sudden it just fell out from underneath us.
Jeff was driving an earth mover when he fell more than 30 meters.
I mean, there wasn't really anything you could do or nowhere to go. You couldn't run or do anything. So I bounced off the piece of equipment that I was on and then cartwheeled off into the water.
Stage by stage, the bridge was collapsing.
The north end of the bridge buckled up 40, 50 feet in the air, slab by slab, like a snake, coming right at me. And it just looked like a monster, the way it took cars and it would buckle up and cars would be suspended in the air and then come back down on the bridge. And when it got to me, my slab, it lifted me up. And I remember looking out over everybody, and then I heard a boom. It was the bridge coming down, and then just 1-2 seconds later, the whole bridge just went down. And I remember screaming out loud, "No, no, no," and I truly thought that was the day I was gonna die.
Andy's car fell 15 meters, but stayed on the wreckage. Lindsay Peterson's car, however, went straight to the bottom of the Mississippi River, with Lindsay still at the wheel.
I was instantly submerged under the water. The water was there right away. I didn't have even this moment to gasp for one last breath of air to sustain me.
Lindsay became disorientated in the murky waters and couldn't find a way out of her car.
You know, it was dark and murky and I didn't really know where I was after a while. But eventually I started to gasp for air, and at that point I was realizing that I was probably getting close to the end of my time down there, like what I could handle, and I hadn't found an escape yet. And so I started, I gasped for air like 4 or 5 times, and at that point started to kind of change my perspective and try to move away from trying to save myself to trying to accept that I was going to die.
For 3 to 5 seconds, it was the most eerie quiet I've ever heard, I guess, if that makes sense. You couldn't hear the wind, you couldn't hear the birds, you could hear absolutely nothing. And for a split second, I questioned that I died. And I thought, that didn't hurt. And then that went away pretty quick.
But construction worker Jeff Ringate managed to swim to a piece of debris.
There's people screaming everywhere, blood and cars sinking, people in them, and rubble and rebar sticking everywhere. It looked like a war zone.
Jeff caught sight of Lindsay and knew he had to act fast.
She was in bad shape. She was in the water. Me and my buddy Josh pulled her out with a broom handle, and she was bleeding and broken back. She was in bad shape.
I don't know how I got out of my car. It's really a mystery. The only clue that I really have is that my fist is filled with scars. It looked like I had punched a window. I don't remember punching a window, though. I would think that I would remember having superhuman strength like that.
Andy Gannon still has nightmares because of what he saw.
The vision of the buckling is what I have the hardest time forgetting. I just can't believe it happened.
I mean, I still sometimes am trying to wrap my head around why I'm alive still, because I thought I was dead. I don't know, and there's no real explanation as to why I'm alive, so it makes it even harder to really come to terms with that.
These were the lucky ones. 13 people died and many more suffered serious injuries. The nation was stunned. How could an ordinary interstate bridge suddenly fall out of the sky? The area was cordoned off like a crime scene, and investigators combed the wreckage for clues. Even veteran bridge experts were shocked.
It was exactly the same reaction that I had when the World Trade Center collapsed. I said, this can't happen.
The incident at Minneapolis scandalized America and severely damaged trust in the country's infrastructure. The I-35 bridge was a 40-year-old steel-deck truss bridge. There are 465 similar bridges across the USA. How many others could collapse?
You can't live in Minneapolis without going over a bridge. It's pretty much inevitable. I just kind of have lost a trust in the world and that's around me, and I started to question, especially anything that's man-made or where man has a hand in it. It really causes me to question, because you think people are doing their jobs and following through with things and making sure it's safe, and then something so incredibly horrible happens to you, and it makes you just wonder.
The inquiry into why the bridge failed is still ongoing, but various theories have emerged. One theory points to a possible design failure. The bridge stood on 4 central piers in the river, and initial inspections have suggested that there might have been an inherent weakness in the plates which held the structure together at these 4 points. It's believed that the gusset plates were half an inch too thin for the load-bearing needs of the bridge. But it wasn't clear whether the mistake had occurred during the design or construction of the bridge. Professor Ted Galambos has studied the history of the bridge.
The bridge was built exactly as it was designed. So the designer specified this thickness for these plates. Why he did this, we will never know, because the person who did the design is long gone and dead. So we can only guess.
So was it basic human error? Did the designer get his calculations wrong?
I think the more likely scenario is that the designer thought it was going to be a different strength steel that was going to go into that joint.
The bridge was built during the American construction boom of the 1960s, and there was a drive to save money by using lower-grade steel. In the I-35 bridge, there was a mix of different steels in the gusset plates.
In structural engineering, you have a constant battle between economy and safety.
Despite the alleged design fault, the bridge stood for 40 years. So why did it suddenly fail? Over time, metal suffers fatigue cracking through repeated stress. It's been estimated that the I-35 was pounded by 17 million trucks during its lifetime. Exposure to the elements also makes bridges victims of corrosion, which eats away at the metal structure. Minneapolis has the most extreme temperature swings of any city in the United States. In winter, temperatures can plummet to minus 30 degrees Fahrenheit. De-icing systems had been in place on the bridge for several years using potentially corrosive chemicals. By contrast, on the day of the collapse, the temperature was a sweltering 100 degrees Fahrenheit, which would cause the metal structure to expand. In addition, the bridge was undergoing repair work, and the contractors had equipment and materials on the bridge, adding extra load.
I'd been there about 3 weeks. I was underneath it. It was in bad condition.
There were points along the bridge where there was maybe 2-inch slats where you could see through it and see down to the river. So it just seemed really wrong that I didn't understand why you would ever see the river. Like, that just seemed wrong to me.
If the structure had faulty gusset plates, then wear and tear, extra loading and extreme heat could have tipped it over the edge into sudden and massive failure. Furthermore, some experts pointed out that these problems might have been picked up on if the bridge had been more effectively monitored. Bridge Inspector Bart Anderson gave testimony to an interim inquiry.
There aren't enough hours in the workday for 77 inspectors statewide to take care of 14,000 bridges the way we should. Although we have a backlog of structurally deficient bridges and an increasing problem with steel fatigue in many bridges, we're lacking the funding that improves the safety of the bridges.
Emergency tests have been carried out on the 465 similar bridges across America, which might also be vulnerable to collapse. And the bridge builders of the future will need to learn valuable lessons from what happened on the I-35. And in the era of super bridges, failing to learn these lessons could lead to catastrophe on an altogether different scale. Stonecutters Bridge in Hong Kong is one such super bridge. Its magnificent 1 kilometre span will be exposed to everything Mother Nature can throw at it. Standing at the gateway to the South China Sea, it will have to tolerate an exceptionally humid and corrosive environment.
We are in a marine environment, and that brings it with extensive and heavy chloride presence in the atmosphere around the bridge.
To fight corrosion, the engineers are using super durable materials.
We've put a stainless steel top to the tower. This reduces considerably any maintenance at the top of the tower.
The stainless steel skin is of a super high grade and was fabricated in the UK. It'll provide an impermeable layer of resistance to the elements and will never need painting. The concrete used in the bridge is also of a particularly high density to stop chloride penetration. If chloride from salt water gets into the interior of the structure, the steel will corrode and then expand and then crack the concrete. To protect the deck, the inside will be fitted with dehumidifiers to reduce the corrosive atmosphere. For the bridge builders in Hong Kong, the collapse in Minneapolis has sent a strong and clear message.
The bridge collapse in Minneapolis highlighted the importance of a good maintenance regime for any bridges throughout the world. And maintenance of structures is absolutely vital. For example, here in Hong Kong, proactive maintenance has resulted in an infrastructure which operates very effectively without any issues, for example, with bridge failures.
The design of Stonecutters includes a variety of innovations for inspecting and maintaining the structure throughout its life. There will be retractable inspection gantries at the top of each of the towers. There will even be a maintenance shuttle train inside the deck to help monitor the interior of the bridge. Stonecutters is bridge building at its leading edge. This international team of world-class engineers is pooling knowledge from all previous bridge failures to create an invincible structure which will stand for 120 years. And it's not just the bridge that needs to be protected from the elements, it's also the staggeringly high approach roads which will bring up trucks from the nearby container base. Because Stonecutters is more than just a bridge, it's a vital link in a whole infrastructure chain of roads, tunnels and causeways. And its creators need to make sure that it stays corrosion-free for at least 60 years. Back in America, this kind of innovative approach to durability and safety is now being applied in Minneapolis, where bridge builders are working round the clock to replace the fallen I-35. And the new bridge has to prove itself to a suspicious public. For John Chiglow, it's a tough call.
Bridges are not supposed to fall, and there's not supposed to be a collapse like this. And so we have to reestablish that trust and confidence that when people use these facilities, they can use it and use it safely. We've been working around the clock since then, 24 hours a day, 7 days a week. There are no holidays on this job.
Incredibly, the plan is to complete the new bridge within a year. The I-35 is a vital road artery running from Texas to the Canadian border, and it needs to be fixed quickly.
We've estimated that each day this bridge is out of service, there's a $400,000 a day impact to the traveling public. That does not include the impacts to the businesses. That's what really justified approaching this project in this aggressive of a time frame.
To speed up the process, the contractors are using a system known as design-build, in which construction starts before all elements of the design have been finalised.
One of the unique elements of this construction is particular parts of the job continuously going along at the same time as others are being designed. We work at the bottom when we have not yet got what sits on top of it designed, and continuing we work at the piers, whereas we didn't have the design of the deck finalized, and all the way along. We know the order we're going to build things, so that was the same order that we had things designed.
But the speed with which the new bridge is being built has also raised concerns.
Immediately after the collapse of the previous structure, there's initial concerns when we announced the schedule that we anticipated this bridge being built in regarding safety and how we are going to ensure a high-quality structure. And we are not sacrificing quality. Safety is our top priority. Quality comes next. And if you're able to accomplish a safe project in a high-quality manner, schedule will take care of itself.
The man responsible for making design decisions during the fast construction process and for ensuring that the bridge is totally safe is Christopher Burgess.
This bridge is a very stout structure. It's one of the stoutest bridges that I've ever designed and worked on. We are now inside the bridge, directly underneath the roadway deck. You can see here the post-tensioning strand that hold up this span. Each one of these cables right here hold up 1 million pounds worth of tensional force to compress the span.
The new bridge is made out of precast concrete segments known as box girders, and these are held up by a combination of vertical piers and steel cables, which run through the girders, compressing and anchoring the structure. Unlike the old bridge, the new bridge has multiple levels of structural redundancy built into it. In engineering terms, this means that if one or even two elements fail, the bridge will still stand. It's a belt and braces approach to safety.
Also inherent in design is a great deal of repetition and redundant features to avoid any potential issues that happened with the older structure.
The bridge is in fact two bridges, one northbound, one southbound, with two hollow box girders in each direction.
Each box girder is resting on its own pier. Each set of piers is resting in its own foundation. Separate structures, northbound and southbound, are separated by 8 feet. With that separation, one doesn't affect the other. There are many, many post-tensioning strand cables embedded in the bridge. If any one particular cable shows distress, it doesn't mean collapse or failure of the structure. So there's many features to make the structure as redundant as possible. In other words, you make as many possible chances for loads to get down to the foundation.
Unlike the old bridge, the new I-35 will have no Achilles heel, no single point where it could fail and bring the whole structure crashing down. In addition to all the redundant features, the bridge is also being fitted with state-of-the-art smart bridge monitoring systems, which should give early warning of any problems. This constant feedback of information is a feature of modern bridge design. As bridges perform ever more daring balancing acts, engineers need to know how well they're performing in order to avert possible disaster. This is the tallest bridge in the world, the Millau Viaduct in the south of France. Its tallest tower is almost as high as the Empire State Building. Compared to the simple steel structure of the old I-35, this is light years ahead in terms of bridge evolution. The Mayo Viaduct is 3 kilometres long and uses what's known as a cable stay design, in which the weight of the bridge deck is distributed by cables across 7 towers. At this height and length, the bridge is constantly moving, so there are sensors in the pylons, the deck, the cables and the masts to monitor the movement of the viaduct day and night. Mayo is the ultimate in the new breed of smart bridges, a living, intelligent, self-regulating structure. Both outside and inside the viaduct is fitted with its own life support system. It's got its own electricity supply and its own water reservoir and fire hydrants. Should a fire break out on the bridge, firefighters won't have to pump low-pressure water from the town below. The bridge has its own weather station to warn of incoming storms and high winds. And it has an electronic nervous system which constantly reports on the health of the bridge. Thierry Vaissad is in charge of ensuring that all the movements and fluctuations of the bridge stay within safe limits.
Le viaduc il est construit, il est terminé. On pourrait croire qu'il est figé, mais c'est loin d'être le cas. En fait, il est en permanence en mouvement. Et nous sommes là pour vérifier ces mouvements et vérifier qu'ils vivent correctement.
There's so much movement in the bridge's enormous span that the metal road deck can't be permanently anchored to the cliff top. It has to be allowed to slide backwards and forwards over a concrete base.
Donc nous nous trouvons dans le tablier du viaduc de Millau. Au-dessus, vous pouvez entendre le trafic. Le tablier, c'est la partie métallique. Cette partie-là bouge, elle est fixée, elle est posée sur la partie fixe, c'est-à-dire la culée nord où nous nous trouvons. Quand les températures augmentent, le tablier se dilate, il a tendance à augmenter. Quand les températures baissent, il se contracte et il va avoir tendance à repartir. Donc il faut savoir qu'on peut avoir une amplitude maximum de 80 cm, qui est représentée sur cette règle, donc 80 cm, avec 20 cm de marge de part et d'autre, au cas où. Aujourd'hui, nous sommes sur une journée estivale, donc on peut avoir entre 20 et 30 cm de variation sur la journée.
The instruments inside the structure have to accommodate the movement of the deck.
Le chemin de câble, il est monté sur un support flexible qui permet d'absorber justement ces variations. Par ce chemin de câble passent toutes les alimentations électriques, ce qui nous permet de voir vivre le viaduc au quotidien.
Bridge building has come a long way since the days of steel deck truss bridges. Mayo has pushed the boundaries of what's possible. At Mayo, they actually slid the deck out across the valley because it was considered too dangerous to lift it from the ground. Now that it's finished and has become an iconic symbol of French engineering, nothing can be left to chance.
Ici, nous nous trouvons au PC de surveillance du viaduc de Millau. Donc là, c'est le cœur du système. C'est ce qui nous permet de voir l'évolution du viaduc au quotidien.
From here, the maintenance team can monitor temperature, wind speed, humidity and all the stresses and strains imposed on the bridge.
Dès qu'il y a un problème, quel qu'il soit sur le viaduc, ça passe au rouge et il y a un signal sonore qui retentit sur le PC et l'information arrive en clair au niveau du bandeau des alarmes.
Mayo is a state-of-the-art bridge monitored against any eventuality, but it can still fall prey to the elements. If the wind gets stronger than 140 kilometers per hour, the bridge has to be closed for safety. In Hong Kong, the engineers at Stonecutters have to build for even stronger winds, typhoons. And wind is one of the biggest threats to bridges, as was witnessed in 1940 when the world's third largest suspension bridge was brought spectacularly crashing down. Bridges are always at the mercy of the elements. They expand and contract with temperature. They are corroded by rainwater and buffeted by wind. And as bridges try to span ever longer distances, the power of the wind becomes ever more lethal. The catastrophic effect of wind on bridges was dramatically demonstrated at Tacoma Narrows in Washington State, USA.
Last July, the nation hailed the opening of the new $6.5 million Tacoma Narrows Bridge over Puget Sound.
When the Tacoma Narrows Bridge was opened on July the 1st, 1940, it was the third longest suspension bridge in the world. It was a majestic example of the fashion for ever more elegant and slender designs. When the bridge started to sway, people thought there was nothing to worry about. And it remained open to traffic, earning the nickname Galloping Gertie. But 4 months after it opened, high winds slammed into the bridge, setting up a fatal oscillation.
As the great roadway, like a pendulum of doom, swayed and twisted in its death agony.
The bridge then spectacularly collapsed.
There it goes!
just moments after it was closed to traffic. Incredibly, no one was killed, but the designers of the bridge had clearly made a drastic miscalculation.
Suspension bridges in the 1930s had thinner and thinner decks. Mistakes or misconceptions of ideas will come out. You know, whenever there is something not quite right, it will come out. And particularly when you have a succession of bridges where you had success, then you go a little lighter, and then bingo, it fails.
It was later revealed that this marvel of modern engineering had failed because insufficient attention had been paid to aerodynamics. The solid steel plates on the side of the roadway had offered too much resistance to the wind. The Tacoma Narrows Bridge collapse is not only the most famous bridge disaster in history, but also the most influential. Since the Tacoma disaster, all suspension bridges and cable-stay bridges are designed aerodynamically with the aid of wind tunnel tests. Aerodynamics is the study of air movement around objects, and this knowledge grew with the rise of the aviation industry in the 20th century. Nowhere is this knowledge more important than at the massive Stonecutters Bridge, currently under construction in Hong Kong. This landmark $350 million structure will be one of the longest cable-stay bridges ever built, and it sits in a particularly complex and challenging aerodynamic environment.
Hong Kong is quite hilly, the new territories to the north, but to the south, it's actually open fetch across the ocean. So we've actually designed this bridge taking into account two wind loadings. One is when the wind is coming from the south during the summer and it's smooth and less turbulence, but also when the wind is coming from the north. The wind is far more turbulent because it's got to come over the hills, as you see, to the north there.
But most of all, they have to model the bridge to withstand the full force of typhoons, which can reach up to 200 kilometers an hour and bring widespread destruction to the region. At Stonecutters, they had to go back to first principles and test the structure in different laboratories around the world. There were 12 rounds of wind tunnel tests in Australia, Canada, China and Denmark, examining the aerodynamics of the deck, the cables and the towers. The towers at Stonecutters are 300 metres high, as tall as some of the biggest skyscrapers in Hong Kong. Climbing the towers requires 2 construction elevators and takes around 30 minutes. Because the towers are so tall, they'll be particularly vulnerable to typhoon winds. To help combat this, at the top of each tower a huge pendulum will be installed, a device known as a tuned mass damper.
Later on, we are going to cast a slab and then install a tuned mass damper at this part of the tower in order to stop vibration due to wind.
As the tower sways in one direction, the pendulum sways in the opposite direction to stabilise the structure. The main span at Stonecutters will be over 1 kilometre long. This makes it extremely flexible and vulnerable to the wind. Like most modern bridges, the deck is made of hollow steel box girders. Here, they're shaped like aeroplane wings for extra stability. The span also has a unique twin deck design joined by cross girders with a central air gap.
We have a very wide central air gap in this position. Now, this streamlined deck and the central air gap would make the Stonecutters Bridge deck extremely stable against flutter instability, for example. But this central air gap also has a drawback.
The drawback is that while the air gap offers structural stability, it can also create a turbulent vortex of air which hits the downwind deck and causes the whole span to vibrate vertically. A similar problem was encountered in Denmark in 1998. This time the bridge was already constructed and started to display dramatic oscillations even in light winds. The design for the Storabelt Bridge had been tested in wind tunnels, but it was later discovered that at a scale of just 1 to 80, the models were not giving useful information. The problem is that complex aerodynamic phenomena aren't always reproduced in scale model testing, and you can't put the whole bridge into a wind tunnel. Stonecutters learned from the Danish experience and used a much bigger scale model of 1 to 20. The tests showed the likelihood of similar problems with vertical vibration. The solution at Stonecutters was the same as in Denmark. Guide vanes, or metal strips, were added to funnel the airflow around the nearside deck and break the rhythm of the turbulence.
We actually modified the shape of the deck to make it more aerodynamically favorable. And we introduced a pair of guide vanes to suppress the vibration problem.
These guide vanes should ensure that vertical vibration on the deck at Stonecutters will be minimised. Stonecutters will be held up by 224 stay cables, which will also be subject to complex aerodynamic forces. All cable stay bridges produce turbulence because of the way they cut through the air. So the cables also had to be tested in wind tunnels to see how they would perform. Studies have shown that wind and rain combine on the surface of stay cables to create water rivulets which run down the cable and alter the way the cable behaves. And it's not necessarily the strongest gusts or the heaviest downpours which cause most problems. Doris Yao is the stay cable expert at Stonecutters.
When there is rain and it is of medium intensity, and when the wind is not too strong, the rainwater will form a water rivulet on the upper surface of the cable, and the water rivulet actually changes the shape of the stay cables, and in the long run it may even lead to a complete failure of the stay cables itself.
The cables are made of galvanized steel wires which are protected against the elements by a dual layer of high-density polyethylene. It was discovered that a dimpled pattern on the cable's protective skin could counteract the effect of water rivulets by breaking up the flow.
We are confident that by installing the dimples on the cable surface, the rain-wind-induced vibration could be mitigated.
One way to make the bridge less vulnerable to the wind would be to shorten the span by building towers in the water. But that would expose the bridge to a whole new kind of risk, being smashed into by any of the giant container ships that pass beneath it.
Ship impact is a serious design situation for bridges, and there have been a number of collapses of bridges in the past due to ships colliding with bridge piers, particularly in the States. If we were to have a tower in the water, then the chance of the tower being struck during the lifetime of the bridge would be quite high, and we'd have to make sure that the tower could withstand that load. One of the most notable was the collapse of the Sunshine Skyway Bridge in Florida in 1980.
All stations, this is United States Coast Guard, St. Petersburg, Florida. The vessel, Some Adventure, 606 foot, has hit the Skyway Bridge.
In 1980, the southbound span of the Sunshine Skyway Bridge in Florida was destroyed when a freighter collided with one of the bridge's piers during a storm. The impact sent over 400 meters of the bridge plummeting into Tampa Bay and caused 6 cars and a Greyhound bus to fall 50 meters, killing 35 people.
Any vessels in Tampa Bay area, Skyway vicinity, proceed and assist. There are reports of people in the water.
One man survived the fall when his pickup truck landed on the deck of the Summit Venture before falling into the bay.
I seen the ship and I figured it was all over when I couldn't stop. The next thing was I was in the water and I managed to get the door open and I started swimming to the surface and I finally made it up. And I got a lot of water and there was a piece of the bridge there and I held on to that.
That tragic event really marked a major turning point in people's understanding of the seriousness and the consequences of ship impact. After that tragic event, a lot of research was engaged in the 1980s and through into the 90s, particularly in the US, but worldwide, to gain a better understanding of ship impact, both in terms of the way that shipping behaves and the probability of collisions occurring, and also then the consequences of that collision, the dynamics of the ship-bridge impact.
Positioned at the entrance to the world's busiest container port, Stonecutters will be very vulnerable to ship impact. Towers in the water were therefore ruled out. Instead, the designers proposed to support the bridge from the quayside, but they needed to be sure this would be safe. Matt's team studied the movement of traffic in the Kwai Chung container port and carried out a statistical analysis of the likelihood of a ship colliding with the quay wall.
We found that the chance of that was maybe 1 in 300 years, which is too frequent for us to accept without some further study.
Further tests were carried out to model the effect of a ship impact on the foundations of the towers. Such an impact would drive a giant bulb of pressure through the soil, right into the base of the structure.
The impact scenario that we investigated was a 155,000 deadweight ton vessel traveling at 6 knots. That's equivalent to the largest container vessel in the world, traveling at about the same speed as the ship behind us is traveling.
So the team at Stonecutters added extra reinforcement to the top of the foundation piles to give them enough strength to resist that pressure bulb during ship impact.
So we can say with confidence that should one of these super container ships collide with the quay wall, then Stonecutters Bridge would stay standing.
But it's not ships or wind or corrosion which is the biggest destroyer of bridges. The most hazardous time for a bridge is when it's being built. In 1970, the Westgate Bridge in Melbourne collapsed during construction, killing 35 workers.
It fell from a height of 150 feet. According to eyewitnesses, the section of the bridge broke its back along a central seam. There was virtually no warning for the men working inside.
The tragedy occurred when 2 box girders were being connected. The box girders were out of alignment by 4.5 inches, and an attempt was made to force one of the girders into position using 80 tons of concrete blocks. When the blocks were removed, the whole span snapped. The construction of any bridge is always a risky business. Engineers are working with heavy loads at great height, and there's always a battle against the elements and the law of gravity. At Stonecutters, there's the extra hazard of working over a busy shipping lane.
Kwaichung Container Terminal is one of the busiest container ports in the world, and one of the key safety issues for us has been ensuring that we can erect the deck of Stonecutters over the navigation channel without endangering either the shipping or the workers themselves.
The cargo traffic coming in and out of Hong Kong is too important to stop while construction is going on. So during the lift of sections of the deck, a safe working zone is set up, 200 metres by 200 metres, which is patrolled by security boats. The deck sections are constructed in China and delivered to the site by barge. A new 300-ton section is lifted into place by 2 giant lifting frames every 2 weeks.
That means 8:45 we can move out the barge, is that correct?
In charge of the lift is Operations Manager Patrick Chan.
測量唔出緊嚟㗎啦。
Coordinating from above is Englishman Nigel Day.
Okay, you all set?
2 300-ton cranes lower their clamps into place. The barge has to be stabilised in the water using GPS-controlled motors at each corner. If it were to drift into the shipping lanes, the results would be catastrophic.
Okay, Jackie, what pressure have you got?
Each step of the process is coordinated with great care and concern for safety.
Stop, Dixon, stop. 咁我哋可以做個 living operation.
Any problems, and the process is halted.
On, and let me load. Then we load down the spanner beam.
The barge also has to be completely static, so that when the bridge section starts to lift, it doesn't twist on the cables. As they're lifted, the deck sections sag and distort under their own weight. What this means is that at the end of the 30-minute lift, the box girders have to be bent back into shape to fit the rest of the deck.
Okay, what's the gantry wheel? Okay, I'm going to start pulling in 2 minutes.
Once the deck section is level, it's pulled towards the rest of the bridge. The outer edge girders are then forced back into shape using an external post-tensioning system, shaped like a set of goalposts and fitted with 4 500-ton hydraulic jacks. Potentially, it's a similar situation to Westgate in Melbourne, where the bending of box girders caused a fatal collapse of the structure.
Okay, boys, after 3. Yat, Yi, Sam, pull.
The difference at Stonecutters is that every stage has been modelled by computer, and there's close monitoring of the shifting geometries of the structure and the stresses being imposed on it throughout the operation. The bridge builders have learnt from the mistakes of the past and make it look easy.
When you've done that, have a break. Lunchtime, okay?
So we're going to take a lunch? Yeah.
Okay, good job.
Good job, yep.
Nonetheless, when the bridge is only half built, it seems to hang precariously in thin air.
The bridge is not precarious at all. One of the key areas that we considered was when the bridge was cantilevering out over the Rambler Channel. We are focusing very much on the stability and the safety of all workers on the bridge deck at all times during construction. Safety is part of the consciousness of each and every worker on the bridge. A lot of instruments are being put in to interrogate the performance of the structure during the construction process. After every lift of every segment and installation of every set of cables, we have analysed the structure.
After every lift, the new deck section is threaded with cables and connected to the tower. The cables arrive from the factory on giant reels and are straightened out on the deck before being lifted by crane up to the stainless steel tower top. They're too heavy to be manipulated by hand, so they're manoeuvred into place by jacks. A matching cable is then attached to the backspan, so that the extending deck is perfectly supported. Lessons learned from previous bridge failures during construction mean that Stonecutters is completely stable throughout the process. Step by step, this super bridge reaches out to meet its other half across the channel. Stonecutters will be a state-of-the-art bridge representing the pinnacle of engineering achievement. But it's actually just a tiny part of an even more ambitious project. Stonecutters will be just one link in a huge infrastructure chain, which will culminate in a monster 40-kilometre bridge connecting Hong Kong to Macau. When bridges collapse, the images travel around the world and live long in the memory. Shocking bridge failures damage our faith in man-made structures. But bridges are now spanning previously unimaginable distances in ever more ingenious ways. They're crossing oceans and connecting countries. In Hong Kong, there are plans to build a 40-kilometre super bridge to Macau, which will test bridge building to new limits. Construction on this super bridge is scheduled to begin in 2010. It'll be built from a body of knowledge amassed from all previous bridge failures. It'll be designed to be disaster-proof.
There is increasing ambition in design, but safety is always first. We have to make sure that our bridges are strong enough to withstand all of the design loads. So I don't think that increased ambition is being achieved by reducing the margin of safety. It's more by pushing back the boundaries of imagination.
The philosophy at Stonecutters is, if it can be imagined, it can be built, but built safely. In Minneapolis, they've been working round the clock to build a new bridge on Interstate 35 to replace the one which collapsed in 2007. Valuable lessons have been learned, and this time it'll be a much safer bridge, a bridge built from disaster.
Obviously, the events were very tragic, but I think bridges are becoming more safe. We know a lot more about bridge behavior than we did 75 years ago, 50 years ago. I think we're applying these technologies now, like the health monitoring system or the redundant aspects. We're aware of these things, and all these new bridges now incorporate this new technology.
Up to 600 workers have been employed in the new bridge at any one time, including one of the survivors of the 2007 collapse.
That's what I do, so I worked on the new bridge for 6 months and back doing repair, working on bridges.
But not all of Jeff's colleagues have regained their nerve.
Some of them are still not back to work yet. Well, they are all busted up and injured, but some of them, I don't know if they'll ever come back. My buddy Josh, he won't work on bridges anymore. He's doing buildings now, so.
The eyes of the world are on the new I-35 bridge, and it has to be seen to be super safe. For that reason, the designers have been extra cautious. Even though the bridge has been designed to carry 7 lanes of traffic in each direction, it'll only be striped for 5.
I mean, not only have we built it very quickly, we've built it with more quality oversight, probably by a factor of 10 than I've ever seen on a job.
In the early hours of the 18th of September 2008, the new I-35 bridge across the Mississippi River opened to traffic an incredible 3 months ahead of schedule. The bridge builders have used state-of-the-art smart bridge systems to ensure that a repeat of the previous year's collapse never happens again.
Well, there's thousands and thousands of bridges across the nation and across the world, and people have to have confidence when they use that public infrastructure that they're going to be safe when they do it.
It's been estimated that the USA needs to spend $1.6 trillion on its infrastructure in the coming years. Minneapolis has been a wake-up call. In Hong Kong, the ambition to build futuristic infrastructure is balanced by an understanding of the need to constantly maintain it.
Building infrastructure is only a part of the story, and only a small part of the story at that. It's very, very important that authorities actually continue to maintain and operate in good condition this infrastructure to make sure it develops its full potential.
The bigger story is that in the age of super bridges, it's no longer enough to create a magnificent structure. You have to be equally inventive to protect it from disaster. It may be impossible to design a bridge that can withstand every threat, but as massive spans link communities all around the globe, the lessons of past mistakes are being learnt and are helping shape the future. For thousands of years, ships have allowed man to travel the globe, crossing the vast emptiness of the oceans. The rewards for these journeys have been huge. So is the cost when things go wrong.
It's incredible to see what happened. People are drowning in the ice-cold water.
But every disaster has radically changed the design of the ships that followed.
Every single decade, we learn more and more after every casualty.
Designers strive to make their ships stronger and safer by learning from the tough lessons of the past. From classic cruise ships to cutting-edge designs, modern vessels are literally built from disaster. Disaster at sea can be a terrifying and deadly experience. Often miles from assistance of any kind, passengers and crew have only themselves and their ship to rely on. The ocean is an unforgiving environment where there are no second chances. In 1994, 852 people died after the car ferry Estonia sank in the Baltic Sea. In 1990, a fire on board the Scandinavian Star killed 158 passengers and crew. And most famously in 1912, over 1,500 people perished in the icy wastes of the North Atlantic after the Titanic hit an iceberg. These and other tragedies highlight three of the primary risks faced by passenger vessels: collision, capsize, and fire. The designers of all modern passenger ships use every tool at their disposal to limit the risk of these dangers. And this can be seen clearly in Italy, where one of the most high-tech cruise ships ever built is nearing completion. This is Ruby Princess. $500 million, 290 meters long, and over 116,000 gross tons. Built to cruise the Caribbean, it's taken just 14 months to get the ship to this stage. Giorgio Gomiero is the man responsible for this cutting-edge project.
We are going something like 45 meters, 15 decks when we come at the top. Ciao, buongiorno. Ciao. Okay, we are on board Ruby Princess. This is our latest ship that we are going to deliver in a few months. We built the ship piece by piece. This is definitely an handmade product.
With cabins for 4,800 passengers and crew over 19 decks, this ship will be a complete floating city with every conceivable passenger facility built in. There are 5 swimming pools, 7 restaurants, and even a wedding chapel.
Watch your step. This is a bar, and it is a covered area. We have an hamburger bar, we have another bar over there. Of course, this is a public space. It's a passenger ship. There is quite a lot of space to have fun, to have a drink, to take a rest, to have a swim.
Incorporated into this vast vessel are the latest advances in ship construction and safety systems.
When you start with the project, you have also to take in mind all the safety of the ship. And you have to build the ship also taking all these constraints. And you have to respect all these constraints till the beginning.
The process starts with 19,000 tons of high-quality steel plate. This is made into precise shapes by a plasma cutter, and then welded to form sections which piece together to make up the ship.
So we build the ship like a Lego, actually. The ship is built in the dry dock. We have these big sections that are taken in dry dock, they are put together. One big section is going on board. All the sections should go on like this, and the section is then welded and outfitted.
This huge structure is an incredible feat of maritime engineering, built to withstand the awesome power of the sea. Modern passenger shipping is now one of the safest forms of transport on Earth. But it wasn't always that way. April the 7th, 1990. The passenger ferry Scandinavian Star was travelling between Norway and Denmark with 482 people on board. In the early hours of the morning, a fire broke out in an unused accommodation area. The fire gained strength and rapidly spread throughout the ship, producing clouds of thick, toxic smoke in the corridors. Desperate for oxygen, the passengers searched for ways out.
I heard this noise from the fire, and I saw all the smoke coming out from every open door. I remember that it was so much smoke, and it was like a very huge waterfall of smoke. Then I understood that this is a great disaster. This is terrible. People are dying here now.
At 3:20 a.m., with the fire out of control, the captain gave the order to abandon ship. 3.5 hours after the blaze broke out, rescue helicopters reached the vessel. Firefighters were confronted with a horrifying scene. 158 people were found dead. Trapped in cabins and corridors, many of them hadn't even made it outside to the deck. After evacuating the survivors, the smouldering ship was towed to Sweden, where it took firefighters a further 2 days to extinguish the blaze. The fire was later thought to be caused by arson, but however it started, the results were catastrophic. The ship had serious shortcomings that contributed to the disaster. No smoke detectors or sprinklers in the passenger quarters, malfunctioning fire doors, inaudible fire alarms. But these factors alone did not explain why so many died. During the subsequent investigation, 2 shocking discoveries were made. The first was that many passengers simply could not find their way to the emergency exits. The second was that the fire spread incredibly quickly.
The development of the fire came as more or less as a surprise to our investigators. The fire was much more intense and rapidly intense than we expected.
The investigation found a number of causes for the rapid spread of the fire. One was that large parts of the ship's interior had been coated with a highly flammable plastic laminate. But this plastic didn't just intensify and spread the fire, it also gave off highly toxic fumes.
Hydrogen cyanide is a very toxic gas, very dangerous gas, and this is a gas that with low concentrations also could kill people within a few minutes or even a minute. And it's actually the same gas as Hitler used during the war, killing the Jews in the gas chambers.
The hydrogen cyanide given off by the plastic laminate was the direct cause of many of the deaths. This could not be allowed to happen again. All passenger ships built today must adhere to strict rules regarding the type of materials used in their construction. Virtually all the material must be non-flammable and non-toxic. Antonio Bartolini is in charge of fitting out the passenger areas on Ruby Princess.
This is the main theater of the ship, which provides seating for over 800 people. This wall looks like wood. It's actually not wood, but is a thin veneer applied on a not flammable material. Also, the carpet is not flammable and is made in a way that the smoke is not toxic.
Flammable plastic laminates like those used on the Scandinavian Star have been outlawed for use on passenger ships. But another reason for the rapid spread of the fire was more complex, and it concerned information.
Knowledge is everything, and information is critical in an emergency.
The accommodation areas weren't fitted with automatic smoke detectors connected to the bridge, so the crew didn't know that the fire had started on deck 3. So not all of the fire doors in that area were closed, and the fire quickly spread around the ship. The tragedy on the Scandinavian Star would become the catalyst for a new generation of high-tech safety monitoring systems. These are now mandatory on passenger ships, and the one being fitted on board Ruby Princess is state-of-the-art.
All these cables are coming through from all the detection systems on board and they are passing into the safety management system. These systems makes the operator to be able to monitor the ship for fire detection system, water mist heads, and fire doors, watertight doors, so you can always monitor your ship.
The wiring matrix for the ship uses around 2,500 kilometers of cable.
So these cables are for safety systems and all the automations. The cables are on segregated cable trays in order not to interfere the signal cables from the power cables.
The safety management system has sensors in every area of the ship, so it can provide an instant snapshot of an unfolding emergency.
It's sort of remote eyes and ears of the operator. So it's sort of like having a big brother looking over you all the time, all over the ship.
This is one of the benefits of our age. We have technology. We know not just that one fire detector is going off, that multiple fire detectors are going off. Why is that important? It tells the officer on the bridge, this smoke is progressing. This is not a detector failure. Something's going on down there and you need to take action.
Sensors are constantly vigilant, checking for smoke, temperature changes, and flooding. Before Ruby Princess is handed over to the owners, 6,000 smoke detectors and heat sensors across the whole ship must be tested, a 6-month job.
So now he will activate the smoke detector and we will verify the actual alarm. Pre-warning, no? Prima. The alarm is being activated and you see this was the peak of the smoke detection.
If nothing was done about this alarm, the safety management system would take over. Fire dampers would shut, cutting off the air supply to the fire.
Fans have gone from the red color to green color, so from running condition to the stopped condition. We've just stopped the air supply to that part of the ship.
The water mist system would then activate. This is the latest in sprinklers. Pressurized to 150 bar, the water is sprayed as tiny droplets.
It's a matter of minutes extinguishing fire.
Conventional sprinklers are problematic on ships as they allow large amounts of water to collect, which could cause destabilization or even sinking. The advantage of the water mist system is that it can extinguish a fire using very little water. And it's now widely used on many types of ship. The appalling events on the Scandinavian Star had far-reaching effects on the regulations regarding materials and monitoring systems. But the inquiry also revealed a much more fundamental problem with the ship. The evacuation routes were poorly thought out and managed. Many dead ends and twists and turns trapped disoriented people in the thick smoke.
We could see a lot of people dying just aside a fire exit. I think 12 people were found in a corridor with a dead end. And if you go back 1.5 meters from the dead end, there was a fire exit just to the outside, to the open, to the deck. And 12 people were found on the floor, dead.
In response to disasters like the Scandinavian Star, evacuation planning is now considered at the earliest stages of a ship's design. On Ruby Princess and other cruise ships, one of the primary aims is to make sure there's always a way out.
You have to avoid the dead end, and there is a fire here. Naturally, you are psychologically, you try to avoid the fire, so you escape in the opposite direction. If you want to escape in the opposite direction and there is no any other exit, that is a dead-end corridor, and can happen that the people are trapped inside. Nowadays, all the corridor is designed in such a way that you can always find a different means of escape, bringing you in the same state or the same primary route. That is the modern way to design the escape route of a passenger vessel.
During an evacuation, time is critical. To ensure that passengers can escape fast enough, the evacuation routes are tested with computer modelling.
According to the rules, we have 30 minutes for the assembly, for the mastering time, and 30 minutes for the embarkation and abandon ship process.
All the lifeboats are simulated by these areas here, and so we have from the deck of the ship, where the assembly stations are, you can see all people moving and moving from the public spaces into the assigned area that correspond to the lifeboats. So it is possible to check physically with a sample of travel time and speed of the different occupants, how long does it take for the whole population to reach safely the embarkation points?
On this ship, using the specific tools and the software simulation, we can demonstrate that all the occupants can safely be inside the lifeboats in approximately 20 minutes, so having a large margin in comparison with the rules.
The journey towards safer shipping has been a long one, and the disaster which advanced it more than any other is perhaps the most famous shipping tragedy of all time, the sinking of the Titanic. On the 14th of April 1912, with over 2,200 people on board, the Titanic was on its maiden voyage across the Atlantic to New York. She was the biggest passenger steamship of the day. In fact, the largest moving object ever created by mankind. Incredible luxury, combined with great speed, Titanic incorporated two major safety factors in her design. The first was a double-bottom hull, which protects a ship if it hits an underwater obstruction. The second were her compartments, which subdivide the interior of a ship to stop the spread of flooding. These and other design features gave the ship a reputation for safety and inspired great confidence in her passengers and crew. Some even called her unsinkable. But that night, they were proven wrong. Just after 11:40 p.m, the gigantic ship struck an iceberg. She was at least 560 kilometers from the nearest land. As the iceberg scraped down the starboard side of the ship, it caused massive damage.
This damage went for over 90 meters, and it opened up a third of its length of the starboard side.
The ship could have been protected by her double-bottom hull, but the iceberg had damaged the sides of the ship, above the level of the double bottom. As a result, vast amounts of icy water flooded into Titanic. In this situation, her other design feature, compartments, should have limited the amount of water that could enter the ship. But there was a problem. The damage had compromised not one, but 5 of Titanic's compartments, an impossible breach which would sink any vessel. What became critical now was whether she would stay afloat long enough for a rescue vessel to reach the scene. One aspect of the ship's design proved disastrous. As the damaged and flooding bows sank lower into the sea, the rising water reached the top of the bulkheads that formed the compartments, but these weren't completely sealed to the deck above.
The compartments themselves were not fully watertight. They were open at the top. So what happens is, as water goes into one compartment, it weighs down the ship, and if the ship goes down far enough, water will start to pour in to the next compartment. Because it breached 5 compartments, this cascading effect of flooding could not be stopped on the Titanic, and it went down in 2.5 hours.
When the steamship Carpathia eventually arrived at the scene, the Titanic had already gone down, and the majority of her passengers were dead. Over 1,500 people died in the disaster. Many factors are thought to have contributed. The quality of the rivets used in her hull, her high speed in a known iceberg area. And shipbuilders have learnt many lessons from this legendary shipping tragedy. One of Titanic's design features, the double-bottom hull, is still in use. It's still one of the best ways of protecting a ship from damage caused by a collision with an underwater obstruction, and has saved numerous ships from sinking. The reserve inner hull prevents water flooding into the ship. On Ruby Princess, this double bottom is 1.8 meters deep. To get a proper look at the hull, the ship would have to be lifted out of the water and literally cut in half. But just a few hundred meters away from Ruby Princess, there's a new cruise ship at a much earlier stage of her construction.
You can see here actually a complete section of the ship, and you can see how the ship is built.
This gives unprecedented access to view the double bottom.
The first level is the level of the double bottom. The double bottom is 1.8 meters from the keel, and is there in order to give a safety in case of grounding of the ship. On board the passenger ships is actually specified to have a continuous double bottom from forward to aft.
Underneath, the scale and strength of this vast vessel becomes apparent.
Pay attention, because there are a lot of workers. This is the shipyard.
The level of the double bottom is marked on the outside of the ship.
That sign, the T, the sign T, indicates the placement of the double bottom, okay? The double bottom in this case is more or less 2 meters.
Like the double bottom hull, Titanic's other design feature, compartments, are also still used on modern ships, but with several important changes. One of the biggest improvements was to make the compartments absolutely watertight. This is the Fram. Right now, this brand new cruise ship is sailing near Greenland. But this ship isn't trying to avoid icebergs like Titanic, she's actively looking for them. Her passengers want to see these huge ice mountains close up. The Fram has been designed specifically for this type of cruising. Areas of the hull at risk of collision damage have extra thick plating, and the stem at the front of the ship is made out of an immensely strong single piece of steel. But it's her watertight compartments that are the biggest safety factor.
Outside here is seawater. My head now is about 2 or 2.5 meters below water level.
The bulkheads forming the compartments are welded on all sides to the decks and other bulkheads around them, making them completely watertight.
This wall here is a watertight bulkhead. The bulkhead is attached to the deck above. It starts in the bottom of the ship and goes all the way up to deck 3. No water can penetrate through this bulkhead.
Anywhere that pipes or wires pass through the bulkheads, there are rubber seals.
We have bulkhead penetrations that are waterproof. The pipes are sealed into these penetrations. There's rubber, and it's tightened together, so it's impossible for water to penetrate. I guess it's kind of nice if you don't want the ship to sink.
Another lesson learned about compartments after Titanic was that the more compartments a ship has, the less likely it is to sink after a collision.
Today, passenger ships are very highly subdivided, so simply having damage along the side of the ship doesn't mean a whole compartment running the entire width of the ship is going to flood. That flooding may not make it that far because the compartment is so subdivided.
Here on Ruby Princess, there are 19 compartments compared to Titanic's 16. Most of the bulkheads that form them have doors to allow people to move around inside the ship. These doors must be watertight and on Ruby Princess can be closed remotely or locally.
If a compartment is flooding, this sensor will detect the flooding, the eye level on the bilge, and you will get an alarm in the alarm log. And if they cannot stop the flooding, they will communicate to shut down the compartment, close the watertight doors, and permit the compartment to flood safely.
The lessons learned from Titanic are incorporated into virtually every modern ship afloat. But there was one aspect of the disaster that had a bigger effect on safety at sea than any other. It seems unbelievable, but on Titanic, there were only enough lifeboats for just over half those on board.
Because of the Titanic, today the Safety of Life at Sea Convention specifies that 100% of the people on board must be provided with a lifeboat seat. Therefore, you have a 100% capacity, and that requirement has been there since 1914.
For ships like the Fram that operate in remote areas, access to lifeboats is of paramount importance.
We are ready to release lifeboat number 4.
Lower lifeboat number 4 when you're ready.
Okay, you can release. So now we are lowering the lifeboat down to embarking position. So we make it ready for the passenger to embark. And then we will keep on launching it down to sea level. When we are a long way from the coastline and also a long way from other ships, it's of course important to have the equipment that will ensure us to survive as long time as possible. So to have covered lifeboats with food and equipment that you need to survive for a long time, that is absolutely important for us. 150 people can fit in this lifeboat. It seems incredible, but you sit very, very close to each other, and that can also be a plus because of the temperature. Okay, then you can enter the boat. Today is just a drill on how we will do it in an emergency situation. Of course, we hope that we never have to do this in a real situation. The lifeboat is more than good enough to spend time in, but we like it better when we can spend it on fun.
For the passengers of Titanic that did make it to the lifeboats, the ordeal was far from over. They had few provisions and minimal shelter. Many of them died of exposure because the boats were open to the freezing weather. Many lifeboats today are enclosed to keep the occupants out of the wind and spray and have advanced features to aid survival.
In this locker we have fresh water for the one who's in here in the case of an emergency. And there's half a liter for every person every day, 3 days. Inside this locker is a maintenance sheet for the engine. We have drift anchors. We have also food in these boxes. And we have thermal protecting suit, keeps us warm. This boat is basically a life support system in case of emergencies.
Lifeboat provision on modern passenger vessels means abandoning ship is a far more survivable operation, and this is directly because of Titanic. But collision is still one of the primary causes of disaster at sea, and although modern mariners have many tools at their disposal to reduce the risks, sometimes they need a little extra help, particularly when entering or leaving port. This is the Solent, one of the busiest sea areas in the world. Every day, thousands of vessels pass through, come rain, shine, or thick fog.
Yeah, 2 in Southampton, VTS. Good afternoon, sir.
In 1 hour will be the pilot position on North Star Bridge.
White Saint VTS, it's a candle.
Roger, sir. 1345 pilot launch will be with you.
Because there are so many vessels in close proximity, the chances of collision are high, so the 5 staff in this room monitor the area, making sure the vessels stay clear of each other.
This is the operations room in the VTS Centre for the Port of Southampton. It's not exactly the same as air traffic control in that they give much more discrete or distinct orders to aircraft to follow particular distinct flight paths and flight levels. We're providing advice, but it's very much down to the master with the advice of the embarked pilot to get the ship safely into the port.
To monitor an area this big requires a number of different systems.
The systems that we have available to us are radar, obviously, AIS, we use maritime VHF, CCTV, visual, obviously. So basically, as many methods as you can think of, we will use to get information on traffic and to talk to the ships themselves. In general, the difficulty we have in conditions terms is with visibility. We reduce the traffic to single flow to make sure we don't have a conflict between 2 large ships in one of our channels.
Nowadays, it's common in large ports to have such a system.
Thank you very much, sir.
The VTS Centre provides a safety net for ships at risk of collision, but sometimes it's the sea itself which is the enemy. September 1994. The roll-on, roll-off car ferry, Estonia, was on passage in the Baltic Sea. There were 989 people on board. In the early hours of the morning, halfway between Tallinn and Stockholm, the ship encountered extremely heavy weather. Huge breaking waves relentlessly pounded the vessel. The continual slamming of these vast walls of water weakened the assembly of the bow visor used to load and unload cars. Just after 1 a.m., the hinges failed completely, and the visor was torn off. This exposed the open car deck behind and allowed water to enter the vessel. The effects were catastrophic.
Estonia, what's going on? Can you reply?
My immediate reaction was to try and find a way out, or find a life raft, find a life jacket. I could see the water coming onto the ship. I couldn't see a way of getting off, and I could see my life ending at that point, trapped inside the ship.
The ship capsized soon after, and at 1:50, the Estonia disappeared from radar screens. The ship had sunk to the bottom of the Baltic Sea. Helicopters and nearby ships arrived to help those that had made it to the life rafts. Only 137 people were saved. 852 died. The investigation into the disaster had a profound effect on the design and operation of car ferries and concentrated on 2 areas: bow visor arrangements and stability. In the past, stability had always been a problem on car ferries. This is because they have large open car decks, effectively one huge compartment stretching the length and breadth of the vessel. If water somehow got onto this deck and moved around freely, the ship could be destabilized. The phenomenon is called free surface effect, and it works like this. As the ship naturally rolls to one side, the surface of the water will stay level. This means that the water gathers on the low side of the vessel. The result is that the ship's center of gravity is raised, which has a destabilizing effect, sometimes to the point of capsize. sinking of the Estonia wasn't the only time a car ferry had capsized. Just 7 years earlier, in 1987, the Herald of Free Enterprise suffered a similar fate. The ship had just left the port of Zeebrugge in Belgium, carrying 459 passengers and 80 crew.
We arrived by helicopter, we went down in the ship, and it's incredible to see what happened. People were drowning in the ice-cold water. We tried to get them out. It's a terrible thing.
The Herald was less than 1,300 metres from the harbour entrance, but despite being so close to land, many of those on board didn't stand a chance.
The authorities have long since given up any hope that anyone is still alive out here.
193 people died. In this case, the bow doors have been left open, but the results were the same as for the Estonia. Once water was on the car deck, free surface effect took over, causing the ship to capsize. Various solutions to the problem of free surface effect were tried. One of the first were removable bulkheads. These partitions reduced the size of the open spaces on the car deck, limiting how far water can move. But for short journeys, they increase loading time. Another solution, sponsons, are like huge lifebelts for boats, buoyant boxes that fit around the ship to increase stability. But they also increase fuel consumption, and they can make the motion of the ship uncomfortable for passengers. The eventual solution was far more radical and could only be implemented on brand new ships. It required a substantially different basic hull shape. Wider and more box-like under the water, modern car ferries are inherently more stable. The Adventurer was built in 2003. It's one of the most advanced car ferries operating today and employs a wide and box-shaped hull.
The hull shape does make a ship more stable. We are streamlined at the front, but as you come towards the middle, we're very boxy. And just imagine a box in the water, you know. The thinner the box, okay, the more it's going to rock, okay. But the wider the box, the less it will move in a seaway.
As well as having an inherently more stable hull, the Adventurer has been designed with another feature to deal with free surface effect. Drains, or in nautical terms, scuppers. These drains deal with the problem of water on the car deck in the most effective way possible, by getting rid of it.
The important thing is to keep water off that car deck at all costs.
What we have essentially is big drain holes. The water would go down these drain holes into a big holding tank, okay? And the pumps would then be started to pump this water out of this tank. As the water came in, it would be pumped out.
But in the Herald and Estonia disasters, stability was only part of the problem. Bow doors and visors were the other factor. The Estonia used a vertically opening bow visor. These were popular at the time, but had two weaknesses. Firstly, in heavy weather, there's an upward force in the bow visor from the impact of waves, and this imposes a huge strain on the hinges. The second problem was that the bow visor was directly attached to the car loading ramp behind. When the hinges failed on the visor and it fell off, the ramp was pulled down, and this allowed water to immediately enter the car deck. There were no fail-safes.
It was such a shock to everybody, and it was clear that something had to be done, and had to be done very quickly indeed.
Part of the solution to these basic problems was to move away from using bow visors. Most modern car ferries are now constructed using horizontally opening doors. The advantage is that waves hitting the doors push them inward rather than upward, actually making the structure more solid. The second level of protection is to provide a secure watertight bulkhead behind the bow doors. On the Adventurer, this is formed by the car loading ramp. It's entirely separate from the doors, and once raised, is locked in position.
This ramp, when in the fully closed position as it is, forms an integral part of the ship's collision bulkhead. If the outer hull is breached, for example, if we were hit by another ship in the bow area. As long as the bow ramp here integrity is not breached, it should allow no water ingress onto the car deck.
Should anything go wrong with the bow door arrangement, it's vital that the crew know about it. Like the Scandinavian Star, both the Herald and Estonia disasters were made worse by a lack of information.
The Herald and the Estonia didn't even know water was coming into the deck.
The Adventurer and virtually all modern car ferries are fitted with advanced monitoring systems, CCTV, and flooding alarms to alert the crew immediately if water is entering the car deck.
Here we have the water detector alarm. If any water comes onto the car deck, water will flow up into the pipe. There's a sensor inside that detects the water and sets the alarm off both visually and audibly on the hull integrity panel on the bridge, so we can immediately know if there's water on the car decks. Back that up with a visual check on the CCTV.
CCTV system on the ship covers the whole ship, the whole engine room and the whole of the car decks and outside decks. It's very, very beneficial to us in emergencies. If, for example, the bow is breached, you can see straight away down there if there is water.
Systems like this were introduced after the capsize of the Herald. They drastically reduce the chance of a vessel leaving port with its doors open, and also allow the captain to constantly view the status of the bow doors and car deck whilst at sea. Virtually all modern car ferries are built with these improvements, and it's because of what happened to the Herald of Free Enterprise and the Estonia. Thanks to these advances in design, car ferries are now safer than ever before. But ship designers haven't stopped there. There's a radical new type of ship that addresses all of the problems faced by car ferries, the high-speed catamaran.
At the moment we're travelling from Dunleary to Holyhead on the Irish Sea. We're travelling at 40 knots on the Stena Explorer, which is the world's largest high-speed catamaran ferry, which is 126 metres long, powered by 4 gas turbines, which are the equivalent of aircraft engines.
These 4 engines produce a staggering 100,000 horsepower. They drive 4 of the world's largest water jets, which between them pump out 100 tons of water every second. This gives the Explorer a top speed of 40 knots. It's also hugely stable thanks to the 2 hulls being set 40 metres apart. And because it's so wide, cars can perform a U-turn inside the ship and enter and exit using stern doors. This means it has no bow doors. The Explorer is cutting edge and has every imaginable safety system designed in from the start. But this ship has one safety feature that overrides all the rest. In case of a collision that damages the hulls, it'll stay afloat even when inundated with water.
And wreck the ship, which means taking the bottoms out of both hulls, and the ship will still float. She'll float at the car deck level, which is a very safe position to be in.
The Explorer can do this because she's very light, a result of being designed to operate at high speed. While the Explorer seems to be an ideal solution to the challenges faced by car ferries, there's one problem it faces that's extremely difficult to overcome: fuel consumption. The price for such high speed is reduced fuel economy. As a result, the high-speed catamaran sometimes only operates at reduced speed. There will always be a demand for the unique service that ferries offer, so naval architects keep working to develop the ultimate design. In Norway, there's a radical new ship that one day may provide a solution: the X-bow.
This is a totally brand new concept that does not exist in comparison anywhere in the world.
This futuristic-looking design is already in use on commercial ships, but may soon be implemented on passenger ships.
The most important aspect is better heavy weather performance. You can actually pass through heavier seas at higher speeds.
There are 2 reasons why the design can do this. Firstly, this type of bow has volume much lower down than a conventional bow. This means as the ship encounters a wave, the increase in buoyancy is gradual and constant rather than sudden and rapid, as on a traditional ship. This makes the vessel's motion smoother. The second reason is that the X-buoy is not flared. Conventional buoys curve out at the top. The X-buoy doesn't. This means energy isn't wasted trying to push waves out of the way, so a higher speed can be maintained.
Now what we see here is the traditional offshore bow moving in North Sea heavy conditions at 12 knots. And this is the Ulstein X-bow, moving in much larger sea states and even higher speeds than compared to this one. And you can clearly see the difference in how they encounter the waves. Now, the normal traditional bow always tries to push the water up and away from itself, whereas the Ulstein X-bow tries to go through it in a more smooth way, just deflecting water along its side.
In this footage shot in heavy weather in the North Sea, the difference between the two types of ship is apparent. The traditional buoy is lost in a plume of spray as the X-buoy almost glides forward. But testing models of the new design wasn't all plain sailing.
So when we first approached the model test facility, they were kind of skeptical to the concept because they believed that the ship would probably go under as soon as it hit a wave. So we found that we wanted to test the boat in a developed high sea state where you encountered a big wave in high speeds. So this boat is now moving along at 14 knots, hitting a wave at approximately 14 meters. And even in this wave, the boat survived well. And that was a very good day, actually.
One of the primary advantages of the design is that it reduces the slamming effect of waves on the bow.
If you see the gray spot here and here on this vessel, those are pressure cells that measure bow impact loads. And we've seen that the Ulstein X-bow never have any bow impact loads of significance. Since you don't have that continuous slamming impact, you're not as exposed to structural damage as compared to a traditional type bow.
This is a potential benefit for ferries.
We have a separate design that we are now developing for ourselves, and we know for a fact that loading is going to be significantly less than for a conventional flared bow vessel.
The design has several other assets for passenger shipping. Because it's able to operate regularly in heavier weather, there should be fewer cancelled or delayed sailings. And as the ship is subject to less stress, the manufacturers claim that maintenance costs should be lower. And fuel costs will also be reduced because the design moves more efficiently through waves. Maybe one day, all ships will look like this. Back in Italy, the finishing touches are being added to the much more traditional-looking Ruby Princess. When all the onboard systems have been successfully tested and the ship is handed over, the owners will have a vessel that has been built with knowledge that's been gained over hundreds of years. From safety monitoring systems to watertight compartments, even the most sophisticated aspects of her design can have their heritage traced back to ships that have sailed before.
This process of continual improvement will never stop, nor should it. That's what it's all about.
Although accidents will sometimes still happen, naval architects hope that by learning from the tough lessons of the past, modern ships will sail safely into the future.